This is your lecture for Chapter 11. And Chapter 11 is primarily focused on what is referred to as intermolecular forces. Okay, so up to this point in this course, we've been talking a lot about what are actually intramolecular forces, which are the interactions inside atoms between the, different parts of the atoms, electrons and protons and nuclei and all that stuff. But intermolecular forces are attractions between molecules, okay? As opposed to the things that happen inside molecules or atoms. Now we're going to be talking about what happens between one molecule and another. Okay, and there are several types of intermolecular forces. The first of which is referred to as London dispersion. Okay, or most often it's just referred to as dispersion forces. Okay, London dispersion is sort of the proper name. The next on the list are called dipole forces. Okay, followed by hydrogen bonding. Followed by ion dipole. And lastly, and it's not really an intermolecular force, so I'm going to put it in parentheses, ion-ion forces. Okay? Because ion-ion forces are not so much attractions between molecules as they are attractions between ions, which is kind of a slightly different idea. But our main intermolecular forces that we're going to be talking about are these first four. And the London dispersion is the weakest of the forces, and the ion dipole is the strongest of the forces. Okay? Now, why do we care about these attractions between molecules? Well, intermolecular forces affect a lot of physical properties. Okay. Among those are things like surface tension, viscosity. Not really sure why my pen got all skinny right then. Surface tension, viscosity, boiling point. Melting points. Osmotic pressure. And vapor pressure. Okay. So most of these, the stronger the forces, the stronger the physical properties. So stronger forces will equal more surface tension, more viscosity, higher boiling points, higher melting points, more osmotic pressure. The one that's opposite to that trend is vapor pressure, but we'll talk more about that when we get there. Okay, so let's talk about how these forces work. All right, we're going to start with the dispersion forces. Okay, so dispersion forces are quite simply momentary shifts in an electron cloud, in electron clouds. Okay, and the important part about that is that they are momentary, which means they are temporary attractions. Okay, that is a very important aspect as to why dispersion forces are as weak as they are, is because they are fleeting. They're momentary attractions. But they're happening so often with so many different molecules sticking and unsticking from each other that you get a sort of overall effect. Okay. Now, the other thing that's interesting about dispersion forces is that everything can do this. Every molecule can do dispersion. Okay? Because all you need to do dispersion is an electron cloud, and every molecule has an electron cloud. Okay? So when a question asks, what are the possible intermolecular forces for a given molecule? Dispersion is always one of the answers. So let's take a look sort of at a model of this. So if I have a molecule, and so far we've been talking about molecules in a very strict fashion with hybridization and geometries, and we think of them very much in a ball and stick sort of way. But the reality is that they are kind of like balls of electrons, right? Electron clouds. Okay, so each of these represents a whole molecule. Oops. Okay, and these are their electron clouds. Okay, so in our electron cloud, we have a whole bunch of electrons just sort of floating around. Right? They're doing their thing, they're moving, they're being attracted to things, they're being forced away by things. Okay. Now, what happens when we have a momentary shift of those clouds? So I've got my one molecule and I've got my other molecule. And what happens if just for a moment all of my electrons end up on one side of the cloud for each of these molecules? Because they're constantly shifting, right? So if I get that kind of action, on one end of each molecule I've got a negative charge, and on the opposite end of the molecule I've got a positive charge. Okay, and these little squigglies that I'm drawing are Greek symbols that represent charge, positive or negative. So positives and negatives attract. So for just a fleeting instant, I have an attraction. Between my molecules, because I've got a momentary positive and a momentary negative. Right? We've referred to this as a temporary dipole. Okay? And then in the next instant, the cloud shifts again and that attraction goes away. Okay? But this is why dispersion forces are the weakest of all the forces, because they are temporary. Okay? But every molecule can do dispersion forces because all you need is an electron cloud to make it happen. Right? So there are things that affect the strength of dispersion forces. And those main factors are shape and size. Right? So if what you need to do dispersion forces is an electron cloud, which everybody has, and the amount of positive or negative charge depends on how many electrons you have, bigger molecule equals stronger forces. Okay, so let's think about the forces involved between something like C2H6 versus C5H12. Okay, so lots more electrons here. Lots more electrons, bigger molar mass equals stronger dispersion. Okay, so just having more electrons, a big floppy soft cloud of electrons, will afford greater dispersion forces. So size is a factor. The other factor is shape. Right, so let's think about a molecule that looks like this. And imagine all these little lines are hydrogens. I'm not going to draw them all in because that's tedious. Right? So 5 carbons, 12 hydrogens, versus one that looks like this. Right? Both are C5H12. Right? So same molar mass, same amount of electrons, but my boiling point for the branched one is 9.5 degrees Celsius, whereas my boiling point for the long straight one is 36.1 degrees Celsius. Right? So stronger forces are involved here. Okay? It's important to understand that how the forces affect things like boiling point, because in order to boil something, we have to take something in a liquid state and break those molecules apart so that they are free to fly around the gas state, right? So if we have stronger forces, we have to put more energy in to break those forces, and that equals a higher boiling temperature, okay? So we have stronger dispersion here with the long straight one. Right? Why is that? And a way to visualize it, one that has always sort of stuck with me, is imagine tennis balls covered in Velcro versus a 2x4 covered in Velcro. Right? So with the tennis balls, let's see, we've got our tennis balls here. Covered in Velcro, we have about that much let me do this in a different color. We have about that much interaction right there. Okay? But if I'm looking at 2x4s, right, and we're covered in Velcro, if I stick those 2x4s, look at all this space that would be interacting and sticking to each other, okay? And this is the idea between the sort of branched C5H12 versus the long straight C5H12, right? So we've got, these will be harder to separate. Than the tennis balls will, okay? So that's the analogy to equate how shape can affect the strength of intermolecular forces there, of dispersion forces. Okay, so our next intermolecular force results from a permanent dipole. Right? And that results from polar molecules. Okay? With dispersion forces, if the only thing that you can do is dispersion, it has to be a nonpolar molecule. Looking back at our examples here, right? C5H12, these are nonpolar molecules, right? So the only things that they are capable of doing is dispersion, right? But if I have polar molecules, now I have a permanent dipole, right? So if I have a pair of polar molecules, right, that means that I have a permanent positive and negative end to these things. So I get my attraction here. Okay. The important thing is that because this is permanent, I have a stronger permanent attraction. I mean, my dispersion forces are weaker because they're momentary attractions. They're constantly shifting. But if I have a molecule that is permanently polar, then I can have interactions, right? And you all remember that my favorite molecule is water, right? Water does this really well. Right? Let's think about polarity and water. So if I decide whether or not water is polar, oxygen is more electronegative, so it's going to pull the electrons toward it, right? And so I have a net pull. So this is a polar molecule, right? Remember that molecular shape affects polarity, right? Remember that linear molecules that are symmetrical are nonpolar, that sort of thing, okay? So if I have my water molecule here, I'm going to have a negative end and a positive end. So if I have another water molecule nearby, also with its negative end and its positive end, I'm going to have an attraction. Okay? Resulting from polar molecules. That's super, super important. Polar molecules can do this. Okay? All right, so let's look at our next version of things. So our next type of attraction is called hydrogen bonding. Right? Now, something that students often get confused with hydrogen bonding is that we are not specifically talking about a hydrogen bonded to anything, an actual physical covalent bond. We're talking about an attraction that results from a special type of hydrogen covalent bond. Okay? So just because something has bonds to hydrogen does not mean that it can do hydrogen bonding. Okay? So hydrogen bonding is possible if hydrogen is bonded to oxygen, nitrogen, or fluorine. Okay? Right? This no hydrogen bonding from this. Okay? You have to have oxygen, nitrogen, or fluorine bonded directly to a hydrogen. So, the best molecule in the universe. Right? These are examples of molecules that can do hydrogen bonding. Right? Not just these, but these are examples. Okay? So the way hydrogen bonding works, excuse me. The way hydrogen bonding works is that if I have another molecule that can do hydrogen bonding nearby, I have an attraction between the hydrogen and that oxygen. Right? And I also have an attraction between that hydrogen and that oxygen. If I have another one, I have an attraction between that hydrogen and that oxygen, and that hydrogen and that oxygen. You start to see how we can form sort of a framework here. Okay? If I have something else that can do hydrogen bonding, let's have ammonia, for example. I can have attraction there because I have a hydrogen bonded directly to a nitrogen. Okay? So, hydrogen bonding is responsible for ice floating, of all things. It also helps, and because ice floats, that's how our planet helps to maintain temperature and why aquatic life can live through winters when places that it's cold, because ice floats, and ice floats because of hydrogen bonding. Okay, when the water molecules are frozen in place, the hydrogen bonding helps to keep the space between those oxygen molecules, or those water molecules, and that creates a lattice that makes ice less dense than liquid. Okay, which is fascinating. So we can thank hydrogen bonding for life on Earth. Okay, so let's think about strength of hydrogen bonding. So, for example, H2O can accept 2 hydrogen bonds and donate 2 hydrogen bonds. Okay? Because each oxygen can, and I sort of, in my illustration above, I put too many on that top oxygen, but each oxygen can accept 2 hydrogen bonds, and because we have 2 hydrogens bonded to an oxygen, it can donate 2 hydrogen bonds. Right? If I look at something like ammonia in a sort of more three-dimensional version, right? Ammonia can accept 1 and donate 3. All right? So because it can only accept 1 and it's not as strong. All right? So remember, hydrogen bonding is only possible if hydrogen is bonded to oxygen, nitrogen, or fluorine. Okay? Only in those scenarios. Right? So let's do a little prediction. Okay, so if I have a molecule, and we haven't gone over line drawings yet, but I think you'll get the point. If I have one molecule that looks like that, one molecule that looks like that, and one that looks like this, which will have the higher melting point? Okay, we have, in each scenario, we have a hydrogen bonded directly to an oxygen, right? But here we have 1 H bond. Here we have 2 H bonds. Here we have 3 H bonds. Okay, so the one with the more possible, the greater availability of hydrogen bonds will have the higher melting point. Right? Stronger forces. Right? Our next strongest on the list, and it's sort of starting to get away from what is actually intermolecular forces, is ion dipole force. Right, so we're sort of foot half in the door and half out the door with this one. Right, so if we had dipole was an attraction between two polar molecules, ion dipole is the attraction of an ion to a polar molecule. So let's take a look at what that looks like. So if I have some sodium ions in water, okay, I've got sodium ions, and then over here I've got a water molecule that has a positive and a negative side to it. Right? So my negative side of my water molecule is going to be very strongly attracted to that positive ion. Okay? So polar molecules have partial polarity. Ions, on the other hand, only have one half of the pole, right? So they're very, very attracted to things that are polar. And if I have, let's say that I put some sodium chloride in my water, and over here I've got my chloride ion, I will have a very strong attraction to the positive side of the water molecule. Okay. So, but in order to have ion-dipole interactions, you must have an ion present. Okay. Usually that's going to take the shape of situations where you have like some sort of ionic salt in water. Okay, so you have to have an ion in order to have ion-dipole interactions, right? And then our strongest force is ionic interactions. Okay, and that would be, for example, between two ions only. Okay, because we don't have anything messing about. We don't have any temporary shifting of positives and negatives. We don't have even whole molecules that are half positive, half negative. We just have a whole positive and a whole negative, and we're coming together. But strictly speaking, ionic interactions are not interactions between molecules. They're interactions between two atoms that happen to be positive and negative charged. Okay? But they are technically the strongest of the forces. Right? So, evaluating forces. So you'll often be asked to list what forces are possible in a given molecule. And there's a series of questions that you want to ask yourself. All right, so in terms of evaluating forces, right? So first question you want to ask yourself, or first thing you want to acknowledge, let me put it this way. All molecules can do dispersion. Okay? Anything with an electron cloud is capable of doing dispersion. So, next thing to think about, are the molecules polar? All right? And hopefully you are comfortable determining polarity of molecules. Remember that geometry matters. Okay? You can't always just trust a flat Lewis structure. That's why we teach you Lewis structures before we teach you about molecular polarity. Okay? So, if they're polar, you get dipole-dipole possibility. Okay? Next question to ask yourself, is there hydrogen bonded to oxygen, nitrogen, or fluorine? If yes, we get hydrogen bonding. Right? Next question to ask, and this is sort of a checklist for determining what types of intermolecular forces there are. So next question to ask, is there an ion present? Oops. If yes, you can do ion dipole. Right? And lastly, are there multiple ions present? If yes, ionic bonding. Okay, so let's come back to why it's important to evaluate what types of forces and to get an idea of how strong the forces are. Okay, stronger forces hold molecules together with each other. Okay, so stronger forces. So the stronger the forces equals higher surface tension. Higher surface tension, higher melting points, higher boiling points, higher osmotic pressure. And the weird one is that stronger forces mean low vapor pressure. Right? And I promise we will get to the discussion on vapor pressure here in just a little bit. Okay, but for now, we're going to step away from intermolecular forces a little bit, and we're going to look at a new thing, phase diagrams. Okay, and phase diagrams are a pictorial representation of how pressure and temperature affect what state of matter or what phase of matter things are. Okay. So my phase diagram is going to look like this. Let's see if I can draw a nice big one, because it will be helpful. So on the y-axis, we have pressure, right? And pressure increasing that direction. And on the x-axis, we have temperature increasing to the right. Okay. So my phase diagram is going to be divided up into three areas: solid, liquid, and gas. So we're going to come out this way, and we're going to come this way. All right, and in the center, we have a dot, and at the end of this line, we have a dot. Right? Now, solid, liquid, gas. Left to right on our chart, okay, on our phase diagram. Okay, so let's do this in orange. So on the far left, I'm going to have solid, and as I go left to right, I go solid, liquid, gas. Okay, so that whole region. And let's utilize something I haven't done yet. So this whole region over here is all solid. Okay? And this whole region here, that's all liquid. And this whole region right here, that's all gas. Okay? So depending on your material, these lines will take different sort of directions. But the phase diagram is always going to be left to right, solid, liquid, gas. Okay? So what are these lines really representing? Okay, so let's talk about that for a bit. So the lines are phase transitions. Okay? So this line between the solid and liquid, this is delta H of fusion. Okay? And the line between liquid and gas, this is delta H vaporization. And my line between solid and gas is delta H sublimation. Okay, so along the line, you have equilibrium, right? But if I'm looking at transitioning from one phase to another, if I cross from solid to liquid, in that direction, I'm melting. And in this direction, I'm freezing, right? And across my liquid gas line, that direction, I've got vaporizing, rising, right? And coming back the other direction, I've got condensing, right? And across my solid gas line, if I go this direction, I'm sublimating, right? The transition from solid directly to gas is sublimation. And if I go the other direction, we have what's referred to as deposition. Okay, so say for example, I have a solid that is at a particular temperature and pressure. Let's go with the fuchsia, right? So let's say I have a solid that is at relatively high pressure but relatively low temperature. Let's say it's sitting right here, okay, as far as pressure versus temperature. And let's say that I keep the pressure constant and increase the temperature. All right, if I increase the temperature enough, my solid will transition to a liquid. All right. Now, let's say I have a solid sitting right about here. And let's say I keep the temperature constant and lower the pressure very, very far. If I lower it far enough, I can keep the temperature constant and turn my solid directly to a gas. I can sublimate it. Okay, so this is how a phase diagram is useful. I can look at how the changes in pressure and temperature affect solids, liquids, and gases. Now, these two dots that I've drawn in here, okay, one of them, the one in the center, is called the triple point. Okay, and the one at the end of the liquid gas line, this is called the critical point. Okay, and as I'm running out of room on my diagram, I'm going to scroll down just a little bit. Okay, so, and describe what those are. So the triple point, I'm going to continue in this really lovely radical color. The triple point, all three phases, phases doesn't spell with an F, all three phases exist in equilibrium. Okay, so if you can get the pressure and temperature just absolutely right, you will have a state where solid, liquid, and gas are all present in a dynamic equilibrium. Okay, the critical point is also a very cool place. The critical point is where liquid and vapor are indistinguishable. Distinguishable. That word has too many letters. But when the liquid and vapor are indistinguishable, that has its own name. We call that a supercritical fluid. Okay? Where you have a material that has all the properties of both liquid and gas. where it's compressible, but it also can have a definite volume and all kinds of fantastical things. Supercritical fluids are used in all kinds of advanced research. Okay. Now let's talk about transitions. Okay, and I'm going to get away from this wonderful color. Let's do something slightly more tame. Okay, so when we're talking about transitions from one state to another, right? So if I'm going from solid to liquid, otherwise known as melting, okay, I will have Q of the solid equals mass of the solid, C of the solid, delta T. Okay? But all that is warming up the solid. Okay? Think about taking a piece of iron at room temperature, and what do you have to do to melt it? You have to heat it up. And if you heat it up far enough, it will eventually stop being a solid and become a liquid instead. Okay? But once you get to the place where the solid is going to melt, you have a different Q, Q of the transition. Okay? And Q of the transition is moles times delta H of fusion. Right? And at delta H of fusion, the sign will be positive. Okay? Because it takes energy to melt. Right? In order to melt something, we have to put energy in, right? And then once we have transitioned, okay, then we can take that liquid and we can heat it up. Right? So then we'll have Q of the liquid heating, warming up the liquid, and it will have the same form as warming up the solid. Okay? So it depends on which direction you're going. So this step right here in the middle, the transition step, right? Remember that delta H for a reverse process is the same in magnitude but opposite in sign. So melting, we're putting energy in, so delta H will be positive. Freezing is the opposite process, but it'll have the same value, so delta H will be negative, right? Because we're taking energy out. All right, so let's keep on this subject and look at a new type of graph. Okay, so a heating curve. Okay. Heating curves show the relationship of Q to temperature and what phases are what. Okay, so if I have my nice big graph here, right, and on my x-axis I'm going to have Q, and on my y-axis I will have temperature. Okay. And my heating curve is going to take a shape that looks like this. It's going to be a staggered, sort of stair-steppy thing. Okay, so and these lines are supposed to be totally flat. All right, let's imagine those lines are nice and flat. All right, so at this lowest spot, right? So as Q is, next to nothing and temperature is next to nothing, we are at this first ramp up. Let me make a sort of smaller bit here. we are heating the solid. Okay, so imagine that we've got like a block of ice, and in order to melt that ice, I first have to warm up that ice. Okay, so ice doesn't just spontaneously start to melt as soon as you start to warm it up. So you can have ice that is well below 0 degrees Celsius. Okay, so in order to get it to the point where water melts, you have to get it up to 0 degrees Celsius. And then once we get to this first plateau, we have the transition solid to liquid. Okay, so notice at this stage, right, in the transition stage, we have no temperature change. Right? All we're doing is transforming the solid into the liquid, but we are adding heat. Okay, we're adding heat to this situation, adding energy, but the temperature is not changing. Okay? Now at our next stage, so if we're talking about water, let's use water as an example. So at this point, I have a solid at 0 degrees Celsius. Right? At this point on the curve, I have a liquid at 0 degrees Celsius. Okay? So then if I want to get to boiling, right, I'm going to continue on my curve, and at my next ramp, I'm going to be heating liquid. Okay? Right, so at this bend here, at the end of the transition, I've got liquid at 0 degrees Celsius. If I want to boil that liquid, I need to heat it up and get it to 100 degrees Celsius. So at this point in the curve, I have a liquid at 100 degrees Celsius. Okay, so notice we do have a temperature change. All right, let's come back and let's talk about some of these things. So heating the solid, we have a delta T down here, right? And heating the liquid, we also have a delta T. Okay, and then once I get to the 100 degrees C, I'm back to doing another transition. Liquid to gas. No delta T here. Okay. And then once we get to the end of that line, now I have a gas at 100 degrees C. And then once I'm there, I can continue to heat. I can heat up that gas even further. Okay. So the temperature, the heating curve is a really sort of fascinating depiction of phase changes. Okay. So what's nice about it is that we have Hess's law to help us out. So remember, Hess's law says that the delta H for individual steps can be added up to make the delta H for a process. The sum, oh, that's a terrible sum. Sum of the delta H for all steps. Okay. And remembering that delta H equals Q. So if I'm dealing with heating or cooling, I'm in that stage of things, I have Q equals mc delta T, right? Delta T, change in temperature, is the important part, okay? If I'm in the transition, I've got Q equals N delta H. Okay, and this is for the change of phase. Right, so solid to liquid, liquid to solid, or liquid to gas, gas to liquid, the delta H. It depends on which direction you're going, depends on the sign, will dictate the sign on H. Okay, so our total energy for a phase transition, for a process, would be, for example, Q of the solid heating plus Q of the transition, solid to liquid, plus Q of the liquid heating. Okay, so if you were taking, for example, a block of ice at minus 25 degrees C, and you wanted to find out how much energy it would take to transform that block of ice into some quantity of water at 50 degrees C, you would calculate Q for each step along the way, heating the solid, transition to liquid, and then heating the liquid. Okay. So our last topic, and it's the one that I probably mentioned earliest on in this video, was about vapor pressure. Now, vapor pressure, we talked about it, that it's the one of the sort of physical attributes or physical traits of materials that is opposite the rest in terms of how intermolecular forces does it. But it's really not. So what is vapor pressure? So, for example, if we have a beaker of water, right, of liquid water. So on top of that liquid water, and on top of all liquids, there is a very small layer of vapor. Okay, because the molecules at the very top of the surface are able to have enough energy to transition between liquid and gas, liquid and gas, liquid and gas. They just keep going back and forth, back and forth. And so you have this layer of vapor on top of every liquid, right? You just can't really perceive it most of the time. Okay, so the ability, remember, the ability to become gas is dictated by forces. Okay, so strong forces equals less gas, right? So if I have, so when we talk about vapor pressure, I'm trying to stay in a sort of linear conversation here. So vapor pressure is the force of the atmosphere pushing down on that vapor. Okay, so it's quite literally the weight of the vapor on top of the surface of the liquid. Okay, so if I have more vapor, equals more vapor pressure. Okay, so if I have more vapor, I have greater vapor pressure. But if I have strong forces, I have less vapor. Okay, so ergo, strong forces equals less vapor pressure. Okay, because I have less vapor. More vapor makes more pressure. Okay, less vapor, less pressure. Stronger forces, less vapor. Stronger forces, less pressure.